A good test is to use a couple of slits in a barrier, and then you fire the radiation you're interested in through the holes, and you see what happens on the screen on the other side. Let's start off by firing some particles through. You can probably guess what we're going to get. I think that should just about do it. Let's see what we've got. Yes, there we are. A couple of images, one for each of the slits. And so that's what I want you to remember as being what happens when you have particles. How about waves? Well, we can study the behaviour of waves under controlled conditions using water waves generated in this ripple tank. It's just a shallow tank containing water, but it does have a glass bottom to it, and then underneath the apparatus there's a light source. So the light shines up through the glass bottom, through the water waves, onto that mirror, and then onto that screen where the waves cast shadows. The light rings correspond to the humps or crests of the waves, and interspersed are the dark rings corresponding to the troughs. Okay, well, I've got a better way of generating waves than just dunking my finger in. I've got this straight paddle here, which can be motorized. So let's try switching that on. Right, well, now we've got very beautiful straight parallel waves, each of the humps and troughs being separated by the same distance. So that's our source of waves. Now we've got to try them out by passing them through two slits in a barrier, like that. Just stick that in the way of the waves. Give it a chance to settle a bit. Well, there. That's an interesting pattern, isn't it? Let me just try and point out one or two things to you. Along that direction there, you've got waves going all right. But then right next to it is a direction in which there are no waves going at all. You know, there are no light or dark bands along that particular direction. Next to that, you've got waves, then nothing along there, waves along there, nothing, waves. And of course, you get the same thing on the lower part of the screen. Well, suppose we have some arrangement over here for collecting the radiation. What would we expect to get? Well, we'll get alternating regions where there'll be waves and no waves. We would certainly get more than just the two regions of radiation that we would get with particles. Now, when you get something like this, it's called interference. It's what you get when you get waves coming from two sources, these two slits. They come out, they overlap with each other, the crests and troughs all get mixed up, and the net effect of that is to give rise to this interference pattern. So that then is going to be our main test. If we find that when we pass our radiation through two slits that we get more than the two regions of radiation on the distant screen, then we know that we're dealing with waves. Incidentally, I'll give you a warning that we may need to have to alter the separation and the size of those gaps to suit the particular radiation that we're thinking of at any particular time. Anyway, that's the test. Let's now try and apply it to light. Is light waves or particles? Well, if we use a couple of slits like these two here, I think it's pretty obvious what's going to happen. Yes, there we are, a couple of images, one corresponding to each of the slits. So what does that mean? Light is made of particles? Well, not necessarily. Remember what I said, that we have to be prepared to play around with the separation of the slits. Now, in fact, I've got another pair of slits here, very, very much closer together. They're separated by about a tenth of a pinhead in size. And they're also very, very narrow themselves, and so it's very, very difficult to see them. And because they're narrow, we need quite a strong source of light to push the light through those slits. So this time I'm going to use a laser. Let me just show you a beam. We can have some smoke go on it. There we are. Right, now let me put the slits back into position, and you watch what happens on the screen. There we are. How about that? A whole series of spots of light interspersed with regions where there's no light at all. And that clearly is interference. It can't be anything else, and so that points to the wave nature of light. And the only reason that we didn't get that kind of effect over there was that the slits were too far apart so that the waves coming through the two slits just couldn't overlap as they could with this arrangement here. Well, this was one of the really crucial experiments for showing that light was made of waves. Of course, in the past they didn't have laser beams. They had to make do with other sources of light, but essentially it was the same experiment. And there were other reasons for believing that light was waves, and only a fool could doubt that that was the conclusion to draw. But there was such a fool. His name, Albert Einstein. Einstein, of course, knew about all this evidence for the wave nature of light, but what he had in mind was an experiment that just didn't fit. Well, this is it. It's a device called a gold leaf electroscope, and it's used for detecting the presence of electric charge. It consists of a disc, and attached to that is a rod, and then there are two gold leaves hanging together at the bottom. And it's a device which I can demonstrate by charging up. At least I used to be able to demonstrate it by combing my hair. I'm not sure I've got enough hair these days, but oh yes, that's not bad. Okay. What has happened is that charged electrons from the comb went onto the disc, and some of them ran along the rod onto the leaves and then pushed the leaves apart. So when the leaves are in that position, this means that there is electric charge on the device. I can get the charge off very easily by providing a short circuit for the electrons to go through my finger. As you see, the leaves are collapsed. The electrons go through my arm and down to earth. All right, well, let me just charge it up again. But this time I won't touch it with my finger. And I'll leave the electrons on there. And that's where they'll stay unless they get knocked off somehow. And for that to happen, they need some energy. So how about us trying to use light to knock them off? After all, light has energy. So I want you to watch those leaves as I put the light on them. There we are. Well, nothing's happening. Let's move it up a bit. No, still nothing's happening. I tell you what, we've got this very high-powered laser. So let's use that. Let's put that on, and that will really put a lot of energy onto that plate. Oh, no, that doesn't seem to be doing anything either. Let's try just one more light source. This time, a mercury vapor lamp. That emits a kind of bluish-violet light. And also ultraviolet rays, which give you a suntan. Well, still no effect. But note, I've got a glass plate in front of the source, and that has the effect of absorbing the ultraviolet light. Now, if you want a suntan, it's no good trying to get one behind a window. So let me remove the glass and let the ultraviolet light through. And straight away the leaves collapse. So the ultraviolet light is knocking out the electrons. So here we've seen an example of a very weak source of light managing to knock electrons out, whereas the previous very strong source wasn't able to do it. And the only other difference between those sources is their colour. Now, there's no way in which a wave theory can explain a result like that. Clearly, we've got to seek some completely different kind of explanation. The energy in one of those table tennis balls, of course, isn't anything like enough to shift one of those coconuts. It doesn't matter how many he uses, he's still not going to shift it. Something else is required. Despite all the evidence that light behaves like a wave, Einstein proposed that in this last experiment we've been looking at, light actually behaved like particles, and that light of different colours behaved like particles of different energy. For red light, the energy is small. They are the table tennis balls. None of these have enough energy to free an electron from the forces holding it into the metal surface. It doesn't matter how many particles of this light are shone onto the plate. As far as any individual electron is concerned, it is still being struck by a particle incapable of dislodging it. With ultraviolet light, however, we have particles of high energy. These do knock the electrons out. Einstein's explanation, which was made in 1905, the same year as he proposed the special theory of relativity, his explanation was the only way to explain this experiment. Though it seemed wholly contradictory to the wave theory of light, physicists gradually, and in some cases grudgingly, came to accept it. Einstein was eventually awarded the Nobel Prize for this work in 1922. So the understanding of the nature of light became very confused. There were those experiments like the double-slit one which very clearly said that light was waves. And then there was this last experiment which said that light was particles. You can hardly think of anything more different than waves and particles. Perhaps you'll now begin to understand why at the beginning of the program I started to talk about paradoxes in science. Well, the question then arose as to whether this wave-particle duality, as it was called, whether it just simply affected light or whether it went deeper and affected other things. Well, how about that other energy carrier that I mentioned, electron beams, like the electron beams in a television tube. Well, how do we get an electron beam in here? Well, presumably we have to start off with some metal. We know that there are electrons in there because this is made out of atoms and electrons are part of an atom. Incidentally, that is the first reason why we might suspect that electrons are particles, because this is obviously a particle and an electron is a bit of a particle, so presumably it's a particle itself. But anyway, how can we get the electrons out of here so as to be able to form an electron beam? Really, it's quite easy. You have a high voltage across here, and electrons are being pulled out of one of those balls and are going across the gap, leaving a spark, and are going on to the other ball. Essentially, we have the same kind of thing happening in a tube. Here we've got a metal disc rather than a ball, but the same thing applies. The electrons come out of this metal disc, they go across to this other electrode here, and you can probably see a little hole in the electrode where the electrons pass through there and go on down through the tube. Actually, this is a replica of a tube used by J.J. Thomson, who's accredited with having discovered the electron. It's a grandfather, if you like, of the modern TV tube. I won't actually connect that one up because it's a little bit difficult to see the effect with that. I'd far rather show it to you on this modern tube. If we just turn the lights down, we ought to be able to see the electron beam going across the tube. Yes, I think you can see it there. Now, watch what happens to it. Okay, what am I doing? Well, if we take the lights back up again, you'll see what I'm up to. Well, a magnet. Now that actually is very good evidence that what we're dealing with is particles, because it's known that if you have a charged particle moving close to a magnet, it'll be deflected. And I can show the same effect with this other TV screen like this. Great fun, do this for ages. But for goodness sake, don't do it on your own television set if you've got a coloured one, because the effect will stay there forever. And it'll be a good reminder that electrons behave like particles, but I imagine you could do without that. And how about our test that we've used before, the double slit? Well, there it is. And as you can see, it gives rise to two images, one for each slit. Once again, evidence for particles. Except remember, we had to be a bit careful about that test. Remember about the separation of the slits? Well, just take my word for it, will you, that if we use the pair of slits that we had for the laser in the tube, we would once again get just simply two images. But suppose we took that test to its limit, and we used the smallest slits you can imagine. The kind of slits you get in a crystal, where these represent the atoms, layers of atoms, and then you see we can imagine gaps there and there. So that would constitute our two slits. Actually, of course, it's more complicated. There's the third and fourth slit and so on. And there are also slits in this direction, and the whole thing is three-dimensional instead of two. So the interference pattern we would expect to get from here, if we pass waves through that, wouldn't just simply be the spots that we got for the laser beam. It would be some other kind of pattern. But essentially it would show the same kinds of things, namely that you'd have radiation going to certain places on the screen and not to others, and there'd be some kind of alternation going on. Whereas, of course, if we pass particles through there, imagine lots of billiard balls going through there and bouncing off these, you just get a general sort of splurge. So that's the idea. We're going to pass our electrons through something like that. And that can be arranged quite easily by using a metal foil. Now that is sufficiently thin that we can pass the electrons through from one side to the other. And what we do is to place that foil inside this last tube so that it intercepts the beam of electrons. Now actually, I've already done it. I've already got a foil like that inside. So all we need to do is to rotate the tube round to show you what we get. Well, that really is quite extraordinary and very beautiful, I think. A series of rings, light and darkness alternating with each other. Certainly we haven't got the kind of splurge that we might have been expecting had we been thinking we were dealing with particles. That is exactly the kind of interference pattern you expect to get with the kind of lattice that we're passing the radiation through. So regardless of what we've come across before, the evidence of this last tube is that electrons are behaving like waves.